Assalamualaikum warahmatullahi wabarakatuh and a very good day. In this video, we will explore a chapter on simple linear regression and correlation, which is the last chapter covered in SSCE 2193 Engineering Statistics course. In this part 1, we will look at the basic concept of simple linear regression model. Let's look at these part 1 learning objectives that you should achieve at the end of this video. At the end of learning this chapter in this part 1, you should be able to achieve the following learning objectives. The first, you should be able to identify the response and predictor variables. Second, you should be able to write down the simple linear regression model and its underlying model assumptions. Third, you should be able to estimate the model parameters and hence estimate the simple linear regression line or equation. And finally, you should also be able to make a correct interpretation and prediction based on the estimated simple linear regression equation. Regression analysis in general is a very wide and interesting topic used to analyze a relationship between variables. Recall in Chapter 5 on independence test, we had a study on a relationship but between two categorical variables where both variables represent counts or frequencies. In this chapter, however, we have another method to learn about the relationship between one single variable with another one single independent variable. That is what we call a simple linear regression approach, where the two variables are continuous, not categorical, and these two variables have values in intervals. Other regression analysis methods include multiple linear regression, which is an extension to the simple linear regression approach, which relates one single dependent variable to more than one other independent variables. You can also have a multivariate regression analysis, which relates more than one dependent variable to more than one other independent variables. Another type of regression analysis is logistic regression when the dependent variable is binary, or a Poisson regression when the dependent variable is count variable, and etc. Our focus in this chapter, nevertheless, will only be on a simple linear regression, which is the most basic regression analysis approach. You may refer to Statistics for Engineers textbook, pages 141 until 166, for detailed explanation on simple linear regression. Let's look again what simple linear regression, or simply SLR, is. It is a statistical model or equation that relates one single dependent or response variable, denoted by Y, to another one single independent or predictor variable, denoted by X, linearly. In other words, a simple linear regression model reveals a straight line relationship between one response and one predictor variables, where these two variables X and Y are continuous random variables which have values in interval or range. How do you identify which one is a predictor or independent variable denoted by X in blue, and which one is a response or dependent variable denoted by Y in red? In simple linear regression analysis, It is crucially important to identify correctly which one is a predictor variable and which one is a response variable, because the regression of y on x is not the same as the regression of x on y. Let's look at a number of examples here. In a study on whether the assessment scores is influenced by the total number of revision hours, you should see that the assessment scores depend on the total number of revision hours. Therefore, the assessment scores should be the dependent or response variable y, and the total number of revision hours should be the predictor or independent variable x. In the second example, a study on whether a temperature will affect the amount of productivity. Here, the response variable y should be the amount of productivity and the predictor variable should be the temperature. In the next example, to investigate if the weight of solid removed from a particular material depends on the drying time, obviously, response variable y should be the weight as it depends on the drying time, and thus the drying time should be the predictor variable x. In the last example, to investigate if a car maximum speed is related to its engine power, here y is clearly the car maximum speed, whereas x is the car's engine power. From these four examples, you should be able to notice that the response variable y is the uncontrolled variable where its values depend on another variable. The independent or predictor variable x, on the other hand, is a control variable where you can control its values. For example, you can control the number of revision hours in the first example, or in the last example, you can control the engine power. However, what will the y value, or to be precise, the predicted y value for a given x value? This is what you will explore in this chapter on single linear regression analysis. The simple linear regression model is given as follows, where yi is the ith observation from the response variable y, xi is the corresponding ith observation from the predictor variable x, and the notation alpha in the regression model is the unknown regression coefficient representing the intercept. Please do not confuse between this alpha in the model and the level of significance alpha commonly used in a statistical test. The next notation is beta, which is another unknown regression coefficient representing the slope, and the last term is the epsilon I, which is representing the ith random error for all I from 1 to n, where n is the sample size, which is the number of paired sample data xiyi in this simple linear regression analysis. Since alpha and beta in the simple linear regression equation are unknown, how do we estimate alpha and beta in order to get the estimated regression equation denoted by y cap or y hat? We can do this by using a method of least squares. When we use the method of least squares in estimating the simple linear regression model parameters, we need to have the following underlying model assumptions. First, the errors are assumed to follow a normal distribution with mean 0 and variance sigma squared. Second, the error variance sigma squared is an unknown constant. And third, the errors are independent and uncorrelated, that is, the covariance between the two errors epsilon I and epsilon j is 0. Notice that besides the intercept coefficient alpha and the slope coefficient beta, we have another unknown parameter in this simple linear regression model, which is the unknown error variance. What is the estimate of this error variance? You will also learn how to obtain the estimated error variance in this chapter. To illustrate the estimated simple linear regression equation, please refer to example 7.3 in the Statistics for Engineers textbook, pages 150 until 153, given as follows. After you identify the independent or predictor variable x and the dependent or response variable y, you can then plot the paired observed values from these two variables x and y on a scatter plot where the x values will be on the horizontal axis and the y values will be on the vertical axis. So you will have a scatter plot of y on x or y against x, which looks like this for the data in example 7.3. From the scatter plot, you can observe that there seems to be a negative linear or straight line relationship between y and x for this example. Since the larger the x value is, the smaller the y value tends to be. Therefore, this negative straight line relationship can be explained by this straight line, which is the estimated regression equation given by y hat equal to alpha hat plus beta hat times x, where beta hat is expected to be negative for this example 7.3. So again, in general, what is alpha hat and what is beta hat? Let's proceed to the next slide to see how to obtain these estimated parameters. Let's look closer at the scatter plot for example 7.3 again. Suppose the estimated regression line is given by this straight line. For this observed point, we have the observed xi value and the observed yi value. At the same xi value, you also have the estimated yi value on the straight line. The difference between yi and y hat I is the ith error, or residual, denoted by ei for this sample data. To obtain alpha hat and beta hat by the method of least squares is by minimizing the sum of squared errors or residuals with respect to alpha and beta, that is by getting the partial derivatives of the sum of squared errors with respect to alpha and beta and equate them to 0, which leads to two normal equations. Solving the two normal equations simultaneously, then you will get the estimated intercept and slope given by alpha hat and beta hat respectively. You may want to look at the detailed estimation procedure in the Statistics for Engineers textbook, page 146 until 149. Fitting the simple linear regression model by the least squares method, you will get the estimated regression line or equation given by y hat equal to alpha hat plus beta hat times x, which is a straight line where alpha hat is given by the mean of y bar, minus beta hat, multiplied by the mean of x, which is x bar, whereas beta hat is given by the ratio of sum of products Sxy to the sum of squares due to x, denoted by Sxx. The sum of products Sxy is by formula given by the sum of x times y minus the sum of x times the sum of y over the sample size n, whereas the sum of squares due to x, denoted by Sxx, is given by the sum of x squared minus the sum of x squared over the sample size n. All these formulae are available in the statistical table booklet, page 4. You can actually use your scientific calculator to obtain the values of all elements in the alpha hat and beta hat formula. In fact, you can also get the values of alpha hat and beta hat directly from your calculator. Let's look at how you can do that. The Statistics for Engineers textbook provides the steps of using a scientific calculator from Model 570MS in page 149. What you can do first is to press the mode button twice, followed by 2 and 1 so that you get REG on your calculator screen, where REG is for simple linear regression. Once you have REG on your calculator screen, now you should be ready to insert or store the PET sample data in your calculator by inserting xi value followed by a comma and then yi value followed by pressing the M+ button. You need to do this pair by pair very carefully. As you insert the PET values, you can see that the sample size n increases one by one until you reach the actual n value after you have inserted all PET xi yi values. For example 7.3 that you had earlier, you should have n equal to 10 after you insert all the data, because you have only 10 PET values for this example 7.3. If you want to insert a new dataset using 570MS model, you need to clear or remove first the old data by pressing the Shift button followed by Mode button and then press 1 and finally the Equal button to clear all the previously stored data before you can insert the new dataset for another regression analysis. For Model 570ES, however, you can start by choosing Stat from your calculator main menu. Next, press number 2 button where you can see A plus BX for simple linear regression analysis. Then immediately you will have the environment to insert your data. So now you can insert your data, where in the first column should be for the values of x, whereas the second column should be for the y values. Make sure you insert the pairs of values correctly. Next, for 570ES model again, after inserting the data, you can press a C button and next Shift 1 followed by 3 to get the values of the sums and Shift 1 followed by 5 to get the estimated values directly. Back to Model 570MS, you can follow the next slides for more information, whereas for other more advanced calculator models, I would suggest you to look at your calculator manual or watch YouTube videos on how to perform a simple linear regression using your advanced calculator. Refer to example 7.3 again. The question is, obtain the equation of least squares regression line of y on x for the following data. What you need to do when getting this kind of question are as follows. First, insert the data into your calculator straight away, pair by pair, correctly. Next, you can obtain and list down all summary values directly from your calculator. And finally, solve the question, which is to obtain the straight line equation represented by y hat equal to the value of alpha hat plus the value of beta hat times x, where the values of alpha hat and beta hat are obtained from your calculator. To get the estimates of alpha and beta, you can either use the formula and calculate from there, or you can quote the estimated values directly from your calculator and insert those values in the straight line equation. Based on 570MS calculators, you may press the related calculator buttons or operators to get the values of necessary elements as listed in this table. The S-sum here is above button number 1, whereas S-var here is above button number 2. Therefore, to get the sum of x squared, say, you can press the shift button followed by S-sum and then press button 1 and button equal. Please check if you get the sum of x squared value equal to 20,125. You can also check other values like the sample size denoted by n, the sum of y squared, and so on. Please check if you get the sum of x times y is 26,330, whereas the sample mean for y is given by 68.1. As mentioned earlier, you can get the estimated values of alpha and beta directly from your calculator. Again, by using a 570MS calculator, you can obtain the estimated alpha value by pressing the following operators. It begins with pressing the shift button followed by the number 2 button, which has S-var above it, and then press the arrow button twice, followed by pressing number 1 button and then the equal button, which gives you the estimated alpha value denoted by capital A in the calculator, given by 121.9333, which is correct to 4 decimal places. You can also try to find the estimated beta value denoted by capital B in the calculator by pressing these operators, which should give you the estimated beta value equal to negative 1.2667. Therefore, the fitted, or sometimes we call it the estimated or the least squares simple linear regression equation or simple linear regression line, given by y hat equal to 121.9333 minus 1.2667 times x, which is exactly the answer to the question posted in the previous slide. Once you get the estimated simple linear regression equation given by y hat equal to alpha hat plus beta hat times x, what can you infer or interpret from this straight line equation? Well, the interpretation you can make based on this fitted or estimated simple linear regression equation can be as follows. A unit change in the predictor or independent variable x is expected to lead to a beta hat unit change in the dependent or response variable y. For example, if beta hat value is positive, then a unit increase in x will lead to a beta hat unit increase in y. However, if the estimated beta value is negative, then you can make an inference that a unit increase in x leads to a beta hat unit decrease in y. Back to example 7.3, what is the interpretation you can make based on this estimated equation? Well, since the estimated beta, which is the estimated slope, is negative, then the interpretation you can make is a unit increase in x leads to a 1.2667 unit decrease in y. A very important question you may want to ask: why do you want to analyze the relationship between variables? In simple linear regression analysis, for example, why do you want to analyze the relationship between a dependent variable y and an independent variable x? The answer to this question is that from the regression analysis, you are able to obtain the estimated or fitted regression equation that you can use for prediction. That is, you will be able to predict a value of the dependent variable y for a particular value of the independent variable x. Please note that the prediction is only valid if the values of independent variable are within the given range used to estimate the model parameters. Prediction beyond the range of the data, or we call it extrapolation, will be invalid, doubtful, and should not be trusted. The reason is that, in many cases, extrapolation relies on untestable assumptions about the behavior of the data. Therefore, prediction beyond the range of x values may be incorrect if the linear trend does not continue due to the hidden uncertainties. Back to example 7.3, predict y if x is equal to 42. Since 42 is within the range of x values, then to predict y is simply by substituting x with 42 in the fitted regression equation, giving you a value of predicted or estimated y value equal to 68.7319. So in example 7.3, the prediction is only valid if x values are within the given range of 20 until 65 as given in the earlier slide. For another example, please refer to task 7.4 question number 2 in the Statistics for Engineers textbook page 153 and 154. The question is given as follows, where you can see that the dependent variable y is the number of defective components produced by a machine and the independent variable x is the speed of the machine. The collected sample data are listed in the following table and the detailed questions are listed as follows. To solve the questions, what you need to do first is, of course, to insert the sample data in your scientific calculator pair by pair correctly. Next, from the calculator, you can list down all summary values required to solve this simple linear regression problem. After you insert the data in your calculator, you may check if you get the following summaries, where the mean for x is 262 and the mean for y is 51.8. The sum of x squared and the sum of x are given as follows, whereas the sum of y squared and the sum of y are as follows. You can also extract the value of sum of x times y and check if you really have 10 paired data in your calculator, indicated by n equal to 10. You can also write down the values of estimated alpha and estimated beta in the summary list before you can begin to answer the question. To solve part A of this question, x bar and y bar can be stated directly from the calculator, whereas the sums of squares and the sum of product must be calculated by using the formula available from the statistical table booklet page 4. Using the summary values listed earlier, you can then solve for the sum of squares due to x, denoted by sxx, as follows. The sum of squares due to y, denoted by syy as follows, and finally, the sum of products denoted by sxy as follows. Please note that these calculations need to be shown clearly. To answer part B of this task question, you need to show the calculation using the formula to obtain the estimates of alpha and beta before you can compare with the values provided directly by your calculator. Here, by formula, the estimate of alpha is given by the mean for y, which is y bar, minus the estimate of beta, which is beta hat, times the mean for x, which is x bar. So you need to find the estimate for beta first, which is given by sxy divided by sxx. Since you already knew sxy and sxx values in part A, you can simply substitute the two values in the formula and get the beta hat value, which is around 0.2614, and this value is correct to 4 decimal places. If you use this beta hat value in the alpha hat formula, you will get the following value for alpha hat. Now you can compare with the values given directly by your calculator. Notice that while the values of beta hat are the same either from the formula or from the calculator directly, the values of alpha hat are slightly different. This is due to the use of beta hat value, which was rounded off to 4 decimal places. If you do not round off the beta hat value in the alpha hat formula, then you will get this estimated alpha value, which is exactly the same as what is given by the calculator directly. Therefore, for a calculation like this, it is advisable not to round off any value at the early stage of calculation to reduce the round off error as much as possible. For question in part C from task 7.4 question 2, since the estimated values of alpha and beta have already been calculated or obtained directly from calculator, you can simply write down the fitted simple linear regression model or equation as follows, which is obviously a straight line with an intercept of negative 16.6914 and the slope of 0.2614. Finally, for part D, you can substitute x, which is the speed, with the value of 380 in the fitted regression equation answered in part C, to estimate y, which is the number of defective items produced by the machine, which eventually give you the estimated number of defective items produced by the machine is around 83 items when the machine speed is 380. Please note that the unit for x you use to estimate y must be the same or consistent with the unit for x used in the given data. For example, in this task question, if the unit for speed in the data was given to be as the number of items produced per hour, then the unit of x used to predict y must also be the number of items produced per hour. But if you want to predict y when x is the number of items produced per minute, then you need to change first the value of x to be in the same unit as in the data before you can predict y, so that y will be correctly predicted. We are now at the end of part 1 for chapter 7 on simple linear regression and correlation. Let's look at this part 1 learning objectives. At the end of this part 1, you should now be able to identify which one is a response or dependent variable, commonly denoted by y, and which one is a predictor or independent variable, commonly denoted by x, in a simple linear regression analysis. Next, you should also be able to write down the simple linear regression model with the random errors inside the equation, as well as its underlying model assumptions when you want to estimate the model parameters by using the least squares method. Thirdly, you should now be able to use the relevant formula and your calculator to estimate the simple linear regression model parameters and hence obtain the predicted or estimated simple linear regression line given by y hat equal to alpha hat plus beta hat times x. And you should now also be able to achieve the last learning objective in this part 1, which is to make a correct interpretation and prediction based on the estimated simple linear regression equation. Now, what about constructing a confidence interval for the slope parameter beta? What about testing the significance of regression or the existence of linearity in the model? What about performing the regression analysis by using Microsoft Excel? And what about finding the correlation between X and Y? All of this will be discussed in the other parts of this chapter 7. Until then, Assalamualaikum warahmatullahi wabarakatuh, and see you again in the next part very soon. Thank you for watching and bye for now.